Good afternoon, everyone. How is everyone doing today? Can everyone hear me? That's good. Um, just a few updates. So, I'm senior classes. So, unfortunately, I've received an email last week, Thursday, that our Tuesday classes will move an hour later due to a clash with one of the COS subjects. So unfortunately, that is out of my control. So on Tuesdays, our classes will be from 3:30 p.m. to 5:30 p.m., but that's only on Tuesdays. We still have our normal time slots on Monday, that is from 2:30 to 4:15. And then I also saw an email that classes will still remain for undergraduate modules online for now. Seems like that the protests has gotten out of hand this morning, and the police service had to utilize tear gas and rubber bullets. So please be safe when going to campus, and if possible, please rather have online sessions. Do you guys have any questions so far? So this is an elective for me, but now it clashes with another module of mine. On which period does it clash? Or which day? Both. Please send me an email stating where does it clash, how does it clash, and then we can work something out. Awesome. So if you guys had a clash or something happening, please email me so we have a paper trail, and I'm sure we can work something out. So do you think classes will be online for this whole week? I assume so. So the last communication I received from the head of the department stated that all undergraduate modules will be online until further notice. So I assume it's going to be everything's going to be online until there's a communication from the chief operations or vice chancellor that classes will be online. So why were we online last week? Also due to protest action. So last week, Monday and Tuesday, I couldn't get access to um, campus. So the week before that was orientation week, and then the protest was still quite relatively quiet, but things now seems to be out of hand. You guys have any questions? Anything from the last lecture that you want me to go through? Before we start today's lecture, have you guys looked at the assignment guide I provided you guys? Okay, so I thought I will go through the assignment guide now with you, explain a few things, and if you have questions, then you can ask. So one thing is this is quite a relatively easy assignment, but it takes a while to complete. So do not underestimate the assignment and start as soon as possible. So can everyone see the slides? Awesome. So you have to do this assignment before the 20th of May when you need to submit it through Turnitin. And for this assignment, you will observe the moon for 10 consecutive days and then draw it on a piece of paper. So let's see where I've done that. So what we'll do is you will pick a date and then you will observe the moon for 10 consecutive days. And so then you will use a piece of paper, you can draw it, you can sketch it, you can draw it digitally, you can take photos. Then observe the moon every day for that 10 days on the exact same time. So if you pick 5 o'clock in the afternoon, then you will observe the moon every day for 10 days at that specific time, and then draw on a piece of paper where the moon is. And as you continue on with your observations, you will see that the moon will shift every day. So you have to do a little bit of research to determine when will be the optimal time to do your observation. And then you need to, what you discover, you need to write it in a scientific paper. I've submitted a few articles online for you for reference and examples. One thing is, I state here too, you can use 3 or 4 pages. You're more than welcome to go above the maximum. That is just to force everyone to at least write something. I've also submitted a LaTeX template that you can use. You can use Word or LaTeX, it doesn't matter. Question I want to ask in terms of drawing the moon, are we supposed to do it like how it's done on the example sheet? So what would be the easiest way to show you guys? Let me show you one of the previous year's assignments. Let me quickly find one I can show you. And not this one. Yeah, this can do. So I'll show you 2 examples of previous year's assignments. Let me quickly just upload it so I can show it to you guys. There is the one. There's that one. It's just converting. Okay, I'm going to show you this one. Can you all see my screen? So you're supposed to write an article, and as you can see, this is the scientific article. Here is a picture, a scale drawing of the surroundings and how the moon's position differ every day. So here's the questions I ask you to also answer in the article, and here's another picture of the student's observation. So let's go to a second example I want to show you guys. So this is from a different student. So here you'll see how so I've provided you with examples of how the article should look. You have your heading, who you are, who are you affiliated with, your abstract, your keywords, and then double column. So you can see here the students provided a little bit more background. Here's the students' observations. Here's a bigger picture of the students' observations and the references. So the idea behind this assignment is you write the scientific article of what you observed, and then in your article, you have to answer a few questions. And then one of the key points also of the article is you have to determine what is the diameter of the moon. And you can do that in a couple of different ways. There is a couple of methods that you can use. But the idea is that you guys do a bit of research. It's a small research project, and you figure out by yourself how to do it. So let's go through the marking guide, and I will show you how I will mark it. So on this slide. Can everyone see the marking guide? Awesome. So in a marking guide, the assignment is going to count 100 marks. The first thing is the questions. So if you go through the assignment guide, there's about 4 or 5 questions that you need to answer. Did you answer the questions in your article? So this is open for interpretation, how you want to answer. You literally can incorporate it into your article itself. Or in your article, you can literally have a heading that says questions and then answer it under questions. Then the second thing is observations. That is an easy 10 marks. Did you do your observations? In your observations, can I see the phase of the moon? That's also important. Then I'm going to give 10 marks for logic and background information. 10 marks for the calculation of the diameter of the moon. That is also very easy marks. 10 marks for research. So in your article, did you actually do research? Why does the moon move the way it does? How did you calculate the diameter of the moon? And what's interesting things that you realized during your observations? Then your conclusion, that is also important. So your conclusion is a paragraph or 2. So that's also easy marks. Referencing is also important. You can use any reference style you wish to use. I prefer using the IEEE referencing method, but you can use whatever you feel up to. Then format and layout. I want it in the guide I specified and also as in the examples. So that's also another 10 marks. Editing, spelling mistakes, grammar mistakes. And also, how does the article look? Does it look in standard and do you follow the rules that an article must look like? Also another 10 marks. And then what scientific content did you discuss in your article? So that is really easy marks that you guys can get. You guys happy with this? So which method did I? So I prefer the IEEE. Let me paste in the chat IEEE method. So you can use any method you want to use. You can use the Harvard method. You can use the Scholar method. Any method you want to use, you are more than welcome to. I personally prefer the IEEE method, but you're more than welcome to use any method. And then one last thing I want to show you guys, it is very, very, very important the correct date and time to start your observations. So I'm going to share a screen of, you can just Google when the moon rises and set at your location. So where is that tab? I want to share this tab. Can everyone see the tab that I'm sharing? Okay, awesome. So right now we can see it is now the 26th of February. So when you click on the 26th of February, here we see the moon set at 7:28 morning, moon rises at 9:56. And right now, currently, that's not a good place to start our observations. So let's go to the 29th, also not bad. That's also bad. Let's go to March. So on the 5th of March, you can see here on the graph, the highest point the moon is at is around about 7:44 in the morning. The moon sets at around about 3 o'clock the afternoon, and the moon rises at just after 12 o'clock in the evening. But remember, the moon rise and the set times shifts every day by about 15 minutes. So if, for example, if you want to choose to start your observations on the 5th of March, I would suggest you do your observations around about 1:30 the afternoon. Because if we go now 15 days ahead, the moon only rises at 11:34. So now if we go to 2 o'clock the afternoon, we can see the moon is still above the horizon. But let's do it the other way around. If we go over here now, let's say we want to start our observation let's say at 7 o'clock in the morning. So 7 o'clock in the morning, the moon is almost at its highest peak. But let's go 15 days in advance. 7 o'clock in the morning, the moon hasn't risen yet, so the moon is below the horizon, meaning you need to pick the appropriate time and date that will suit you for your observations. You can do it every day at the exact same time. That moon will be above the horizon. So let's go, for example, to a different date and time. So let's go to the 20th, for example. Here we see the moon starts rising at 4 o'clock the afternoon, and it sets at 1 o'clock the evening. So for this, for example, I would start my observations at 12 o'clock in the evening, because then the moon is still above the horizon. So let's go to the 30th. So 12 o'clock, moon's after 9. So at 12 o'clock, yes, the moon is still above the horizon. Does everyone understand this and how I explained it? So you have about now 3 months to do this assignment. Remember, observe the moon for 10 consecutive days. Plan according to what the weather is going to do, and also plan according to your own time schedule, that you can observe the moon at a specific time every day for 10 days that is above the horizon. Everybody happy with that? Says there's a website. Yes, I'll paste this in the chat. So if you just Google moonrise, set, and rise times, you will find it. So I've pasted this into the chat. And then you can just change to your current location, but it shouldn't differ too much around the Gauteng area. Everybody happy? So can we do appointments to do reviews of a project before submitting it? You are more than welcome. Are you guys ready to start with today's lecture? So before I start with the lecture slides, I thought of showing you guys a few videos just to broaden your mind and to open up your mind to a few of the topics we will be discussing in this lecture. So let me show you the first video. Okay, it's not this one. Let me show you. I'll show that one now. First, I want to show you the universe's size. That is cool, right? So that gives you quite an idea of how big the observable universe is we are working with. So the next image video I'm going to show you is about what we can do with our own eyes and naked eye astronomy. Questions. Sorry, sir, I have one more question about the assignment. What if it's very cloudy or it rains for a few days when you want to observe the moon? So if it rains for 1 or 2 days, then you can continue. You just add on 2 more days to your observation. But if it rains for 4 or more consecutive days, then you need to restart your observations to a better date where the weather doesn't play an influence. Does that help? So we have to do it well in advance. Yes, so part of this assignment is that you have to plan in advance and see what will be the best date for your timetable and also weather permitting. It is a pleasure. So now I'm going to show you the next video.
Hey, Phil Plait here. Welcome to episode 2 of Crash Course Astronomy, Naked Eye Observations. Despite the salacious title, nudity is not required. In fact, given that a lot of astronomical observations are done at night, you may want to bundle up. As it relates to astronomy, naked eye means no binoculars, no telescope. Just you, your eyeballs, and a nice dark sight from which to view the heavens. After all, that's how we did astronomy for thousands of years, and it's actually pretty amazing what you can figure out about the universe just by looking at it. Imagine you're somewhere far away from city lights, where you have an unobstructed view of the cloudless sky. The sun sets, and for a few minutes you just watch as the sky darkens. Then you notice a star appear in the east, just over a tree. Then another, and another. And within an hour or so, you are standing beneath an incredible display, spangled with stars. What do you notice right away? First, there are a lot of stars. People with normal vision can see a few thousand stars at any given time. If you want a round number, there are very roughly 6,000 to 10,000 stars in total that are bright enough to detect by eye alone, depending on how good your sight is. The next thing you'll notice is that they're not all the same brightness. A handful are very bright, a few more are a bit fainter but still pretty bright, and so on. The faintest stars you can see are the most abundant, vastly outnumbering the bright ones. This is due to a combination of two effects. One is that stars aren't all the same intrinsic physical brightness. Some are dim bulbs, while others are monsters, blasting out as much light in 1 second as the sun does in a day. The second factor is that not all stars are the same distance from us. The farther away a star is, the fainter it is. Interestingly, of the 24 or so brightest stars in the sky, half are bright because they're close to Earth, and half are much farther away, but incredibly luminous, so they still appear bright to us. This is a theme in astronomy and science in general. Some effects you see have more than one cause. Things aren't always as simple as they seem. The ancient Greek astronomer Hipparchus is generally credited for creating the first catalog of stars, ranking them by brightness. He came up with a system called magnitudes, where the brightest stars were first magnitude, the next brightest were second magnitude, down to sixth magnitude. We still use a variation of this system today, thousands of years later. The faintest stars ever seen using Hubble Space Telescope are about magnitude 31. The faintest star you can see with your eye is about 10 billion times brighter. The brightest star in the night sky, called Sirius, the dog star, is about 1,000 times brighter than the faintest star you can see. Let's take a closer look at some of those bright stars, like, say, Vega. Notice anything about it? Yeah, it looks blue. And Betelgeuse looks red. Arcturus is orange, Capella yellow. Those stars really are those colors. By eye, only the brightest stars seem to have color, while the fainter ones all just look white. That's because the color receptors in your eye aren't very light sensitive, and only the brightest stars can trigger them. Another thing you'll notice is that stars aren't scattered evenly across the sky. They form patterns, shapes. This is mostly coincidence, but humans are pattern recognizing animals, so it's totally understandable that ancient astronomers divided the skies up into constellations, literally sets or groups of stars, and named them after familiar objects. Orion is probably the most famous constellation. It really does look like a person, arms raised up, and most civilizations saw it that way. There's also tiny Delphinus. It's only 5 stars, but it's easy to see it as a dolphin jumping out of the water. And Scorpius, which isn't hard to imagine as a venomous arthropod. Others, well, not so much. Pisces is a fish? Yeah, okay. Cancer is a crab? If you say so. Although they were rather arbitrarily defined in ancient times, today we recognize 88 official constellations, and their boundaries are carefully delineated on the sky. When we say a star is in the constellation of Ophiuchus, it's because the location of the star puts it inside that constellation's boundaries. Think of them like states in the US. The state lines are decided upon by mutual agreement, and a city can be in one state or the other. Mind you, not every group of stars makes a constellation. The Big Dipper, for example, is only one part of the constellation of Ursa Major, the Big Bear. The bowl of the Dipper is the bear's haunches, and the handle is its tail. But bears don't have tails. So astronomers might be great at pattern recognition, but they're terrible at zoology. Most of the brightest stars have proper names, usually Arabic. During the Dark Ages, when Europe wasn't so scientifically, it was the Persian astronomer Abd al-Rahman al-Sufi who translated ancient Greek astronomy texts into Arabic, and those names have stuck with us ever since. However, there are a lot more stars than there are proper names, so astronomers use other designations for them. The stars in any constellation are given Greek letters in order of their brightness. So we have Alpha Orionis, the brightest star in Orion, then Beta, and so on. Of course, you run out of letters quickly too, so most modern catalogs just use numbers. It's a lot harder to run out of those. Of course, just seeing all those faint stars can be tough, which brings us to this week's Focus On. Light pollution is a serious problem for astronomers. This is light from street lamps, shopping centers, or wherever, where the light gets blasted up into the sky instead of toward the ground. This lights up the sky, making fainter objects much more difficult to see. That's why observatories tend to be built in remote areas, as far from cities as possible. Trying to observe faint galaxies in sky conditions is like trying to listen to someone 50 feet away whispering at you at a rock concert. This affects the sky you see as well. From within a big city, it's impossible to see the Milky Way, the faint glowing streak across the sky that's actually the combined light of billions of stars. It gets washed out with even mild light pollution. Your view of Orion probably looks like this, when from a dark site, it looks like this. It's not just people who are affected by this either. Light pollution affects the way nocturnal animals hunt, how insects breed, and more, by disrupting their normal daily cycles. Cutting back light pollution is mostly just a matter of using the right kind of light fixtures outside, directing the light down to the ground. A lot of towns have worked to use better lighting and have met with success. This is due in large part to groups like the International Dark Sky Association, Globe at Night, The World at Night, and many more, who advocate using more intelligent lighting and to help preserve our night sky. The sky belongs to everyone, and we should do what we can to make sure it's the best possible sky we can see. Even if you don't have dark skies, there's another thing you can notice when you look up. If you look carefully, you might see that a couple of the brightest stars look different than the others. They don't twinkle. That's because they aren't stars. They're planets. Twinkling happens because the air over our heads is turbulent, and as it blows past, it distorts the incoming light from stars, making them appear to slightly shift position and brightness several times per second. But planets are much closer to us and appear bigger, so the distortion doesn't affect them as much. There are 5 naked eye planets, not counting Earth: Mercury, Venus, Mars, Jupiter, and Saturn. Uranus is right on the edge of visibility, and people with keen eyesight might be able to spot it. Venus is actually the 3rd brightest natural object in the sky after the sun and moon. Jupiter and Mars are frequently brighter than the brightest stars, too. If you stay outside for an hour or two, you'll notice something else that's pretty obvious. The stars move, like the sky is a gigantic sphere wheeling around you over the course of the night. In fact, that's how the ancients thought of it. Measure it, you'd find this celestial sphere spins once every day. Stars toward the east are rising over the horizon, and stars in the west are setting, making a big circle over the course of the night, and presumably day. This is really just a reflection of the Earth spinning, of course. The Earth rotates once a day, and we're stuck to it, so it looks like the sky is spinning around us in the opposite direction. There's an interesting thing that happens because of this. Look at a spinning globe. It rotates on an axis that goes through the poles, and halfway between them is the equator. If you stand on the equator, you make a big circle around the center of the Earth over a day. But if you move north or south toward one pole or the other, that circle gets smaller. When you stand on the pole, you don't make a circle at all. You just spin around in the same spot. It's the same thing with the sky. As the sky spins over us, just like with the Earth, it has two poles and an equator. A star on the celestial equator makes a big circle around the sky, and stars to the north or south make smaller ones. A star right on the celestial pole wouldn't appear to move at all and would just hang there like it was nailed to that spot all night long. And this is just what we see. Photographic time exposures show it best. The motions of the stars show up as streaks. The longer the exposure, the longer the streaks as the stars rise and set, making their circular arcs in the sky. You can see stars near the celestial equator making their big circles. And by coincidence, there's also a middling bright star that sits very close to the north celestial pole. That's called Polaris, the north or pole star. Because of that, it doesn't appear to rise or set, and it's always to the north, motionless. It really is coincidence. There's no southern pole star, unless you count Sigma Octans, a dim bulb barely visible by eye. That's not all that close to the south pole of the sky anyway. But even Polaris isn't exactly on the pole. It's offset a teeny bit, so it does make a circle in the sky, but one so small you'd never notice. By eye, night after night, Polaris is the constant in the sky, always there, never moving. Remember, the sky's motion is a reflection of the Earth's motion. If you were standing on the north pole of the Earth, you'd see Polaris at the sky's zenith, that is, straight overhead, fixed and unmoving. Stars on the celestial equator would appear to circle the horizon once per day. But this also means that stars south of the celestial equator can't be seen from the Earth's north pole. They're always below the horizon. So this in turn means that which stars you see depends on where you are on Earth. At the North Pole, you only see stars north of the celestial equator. At the Earth's South Pole, you only see stars south of the celestial equator. From Antarctica, Polaris is forever hidden from view. Standing on the Earth's equator, you'd see Polaris on the horizon to the north, and Sigma Octans on the horizon to the south. And over the course of the day, the entire celestial sphere would spin around you. Every star in the sky is eventually visible. While Polaris may be constant, not everything is. Sometimes you just have to wait a while to notice. And to that point, you'll have to wait a while to find out what I mean by this, because we'll be covering that in next week's episode. Today we talked about what
Does that give a bit of an overview of what we were talking last week about the star brightness and magnitude scale? Awesome. So before we continue our lecture, I'm going to show you one more video about distances in astronomy, and then we will start off with today's lecture. I will provide links on click up to these.
Oh, hey, sorry, I don't mean to be rude. I'm just trying to figure out how far away my thumb is. How? Parallax. Centuries ago, people thought the stars were holes in a huge crystal sphere letting through heavenly light. It wasn't clear just how big the sphere was, but it was pretty dang big. I have some sympathy for them. By eye, and for all intents and purposes, the stars are infinitely far away. If you drive down a road, you'll see nearby flying past you, but distant mountains move more slowly. The moon is so far, it doesn't seem to move at all compared to nearby objects. And it's easy for your brain to think it's much closer, smaller, and actually following you, which is a bit creepy. Sometimes people even think it's a UFO tailing them. Finding the distance to something really far away is tough. It's not like you can just pace off the distance. Or can you? The ancient Greeks knew the Earth was round, and there are lots of ways to figure that out. For example, ships sailing over the horizon seem to disappear from the bottom up, as you'd expect as they slip around the Earth's curve. But how big is the Earth? Over 2,000 years ago, the Greek philosopher Eratosthenes figured it out. He knew that at the summer solstice, the sun shone directly down a well in the city of Syene at noon. He also knew that at the same time, it was not shining straight down in Alexandria and could measure that angle. There's a legend that he paid someone to pace off the distance between the two cities so he could find the distance between them. but more likely he just used the numbers found by earlier surveying missions. Either way, knowing the distance and the angle and applying a little geometry, he calculated the circumference of the Earth. His result, a little over 40,000 kilometers, is actually amazingly accurate. For the very first time, humans had determined a scale to the universe. That first step has since led to a much, much longer journey. Once you know how big the Earth is, other distances can be found. For example, when there's a lunar eclipse, the shadow of the Earth is cast on the moon. You can see the curve of the Earth's edge as the shadow moves across the moon. Knowing how big the Earth is and doing a little more geometry, you can figure out how far away the moon is. Also, the phases of the moon depend on the angles and distances between the Earth, moon, and sun. Using the size of the Earth as a stepping stone, Aristarchus of Samos was able to calculate the distances to the moon and the sun, as well as their sizes. That was 2,200 years ago. His numbers weren't terribly accurate, but that's not the important part. His methods were sound, and they were used later by great thinkers like Hipparchus and Ptolemy to get more accurate sizes and distances. They actually did pretty well, and all over 1,000 years before the invention of the telescope. And I think it also says a lot that these ancient thinkers were willing to accept a solar system that was at least millions of kilometers in size. But at this point, things got sticky. Planets are pretty far away and look like dots. Our methods for finding distances failed for them, for a while at least. In the 17th century, Johannes Kepler and Isaac Newton laid the mathematical groundwork of planetary orbits, and that in turn made it possible, in theory, to get the distances to the planets. But there was a catch. When you do the math, you find that measuring the distances to the other planets means you need to know the distance from the Earth to the Sun accurately. For example, it was known that Jupiter was about 5 times farther from the Sun than the Earth was, but that doesn't tell you what it is in kilometers. So how far away is the Sun? Well, they had a rough idea using the number found by the Greeks, but to be able to truly understand the solar system, they needed a much more accurate value for it. To give you an idea of how important the distance from the Earth to the Sun is, they gave it a pretty highfalutin name, the Astronomical Unit, or AU. Mind you, not an astronomical unit, the one. That's how fundamental it is to understanding everything. A lot of methods were attempted. Sometimes Mercury and Venus transit or cross the face of the Sun. Timing these events accurately could then be used to plug numbers into the orbital equations and get the length of an AU. Grand expeditions were sent across the globe times to measure transits and didn't do too badly. But our atmosphere blurs the images of the planets, putting pretty big error bars on the timing measurements. The best they could do was to say the was one astronomers happy. Finally, in the 1960s, astronomers used radio telescopes to bounce radar pulses off of Venus. Since we know the speed of light extremely accurately, the amount of time it takes for the light to get to Venus and back could be measured with amazing precision. Finally, after all these centuries, the astronomical unit was nailed down. It's now defined to be 149,597,870.7 kilometers. So there. The Earth orbits the Sun on an ellipse. So think of that as the average distance of the Earth from the Sun. Knowing this number unlocked the solar system. It's the fundamental meter stick of astronomy and the scale we use to measure everything. Having this number meant we could predict the motions of the planets, moons, comets, and asteroids. Plus, it meant we could launch our probes into space and explore strange new worlds for ourselves, see them up close, and truly understand the nature of the solar system. And it's even better than that. Knowing the astronomical unit meant unlocking the stars. We have 2 eyes, and this gives us binocular vision. When you look at a nearby object, your left eye sees it at a slightly different angle than your right eye. Your brain puts these 2 images together, compares them. Lied when she said math was useful in everyday life. We call this ability depth perception. You can see it for yourself by doing the thumb thing. As you blink one eye and then the other, your thumb appears to shift position relative to more distant objects. That shift is called parallax. The amount of shift depends on how far apart your eyes are and how far away the object is. If you know the distance between your eyes, we'll call this the baseline. Then you can apply some trigonometry and figure out how far away the object is. If the object is nearby, it shifts a lot. If it's farther away, it shifts less. It works pretty well, but it does put a limit on how far away we can reasonably sense distance with just our eyes. Stars are a bit beyond that limit. If we want to measure their distance Once astronomers figured out that the Earth went around the sun rather than vice versa, they realized that the Earth's orbit made a huge baseline. If we observe a star when the Earth is at one spot, then wait 6 months for the Earth to go around the sun to the opposite side of its orbit and observe the star again, then in principle, we can determine the distance to the star, assuming we know the size of the Earth's orbit. That's why knowing the length of the astronomical unit is so important. The diameter of Earth's orbit is about 300 million kilometers, which makes for a tremendous baseline. Hooray! Except, oops, when stars were observed, no parallax was seen. Was heliocentrism wrong? No. It's just that stars are really and truly far away, much farther than even the size of Earth's orbit. The first star to have its parallax successfully measured was in 1838. The star for astronomers to measure its shift in apparent position as the Earth orbited the Sun. 61 Cygni is about 720,000 astronomical units away. That's a soul-crushing distance, well over 100 trillion kilometers. In fact, that's so far that even the Earth's orbit is and covers about 10 trillion kilometers in a year. It's a huge distance, but it makes the numbers easier on our poor 8 brains. That makes 61 Cygni a much more palatable 11.4 away. Astronomers also use another year, a star 1 parsec. As a unit of distance, it's convenient for astronomers, but it's a terrible one if you're doing the Kessel Run. Sorry, Han. The nearest star to the Sun we know of, Proxima Centauri, is about 4.2 light years away. The farthest stars you can see with the naked eye are over 1,000 light years distant, but the vast majority are within 100 light years. Space-based satellites are used now to accurately find the distance to hundreds of thousands of stars. Still, this method only works for relatively nearby stars, ones that are less than about 1,000 light years away. But once we know those distances, we can use that information on more distant stars. How? Well, like gravity, the strength of light falls off with the square of the distance. If you have 2 stars that are the same intrinsic brightness, giving off the same amount of energy, and one is twice as far as the other, it will be 1/4 as bright. Make it 10 times farther away, it'll be 1/100th as bright. So if you know how far away the nearer one is by measuring its parallax, you just have to compare its brightness to one farther away to get its distance. You have to make sure that the same kind of star, some are more luminous than others. But thanks to spectroscopy, we can do just that. A star's distance is the key to nearly everything about it. Once we know how far it is, and we can measure its apparent brightness, we can figure out how luminous it is, how much light it's actually giving off, and its spectrum tells us its temperature. With those in hand, we can determine its mass and even its diameter. Once we figured out how far away stars are, we started to grasp their true physical nature. This led to even more methods of finding distances. The light given off by dying stars, exploding stars, stars that literally pulse, get brighter and dimmer over time. All of these and more can be used to figure out how many trillions of kilometers of space lie between us and them. And we see stars in other galaxies, which means we can use them to determine the actual size and scale of the universe itself. And all of this started when some ancient Greeks were curious about how big the Earth was. Curiosity can take us a great, great distance. Today,
That is cool, right, guys? So let's continue with our lecture slides. You guys have any questions so far? Do we have a textbook for SCI 154? Yes, we have a textbook. You can just look in our study guide. That is the New Horizons textbook. So last week we ended off with the slides and we started discussing the magnitude scale and what is the apparent magnitude of stars. So with the apparent magnitude of stars is a logarithmic scale. So do we actually need a textbook or the slides suffice? That depends on your study method. I usually recommend getting the textbook. If you know where to look, you'll find a PDF version of it in any case. But my slides are detailed. It depends on how you prepare for your tests. So getting back to the slides. So on this logarithmic scale, we can see the higher the number is, the less bright it is, the more fainter the star is. And if we go to the smaller side, the more brighter the object is. So the Hubble Space Telescope limit is magnitude 26. The human eye is around about magnitude 6. Venus is the 12 okay? Yes, the 12th edition will be okay. Full moon is minus 13. Sun is about minus 26 magnitude. So instead of saying that a star known by the charming name Theta Leonis is third magnitude, they can say it is 3.34. Accurate measurements show that some stars are actually brighter than magnitude 1. For example, the famous star Vega is so bright that its magnitude is 0.03, almost 0. If they are so bright that a modern magnitude scale must extend into the negative numbers. On the scale, famous star Sirius, the brightest star in the sky, have a magnitude of -4, 1.46. Modern astronomers have had to extend the faint end of the magnitude scale as well. The faintest stars you can see with your unaided eyes are about 6 magnitude. But if you use a telescope, you will see stars fainter. Astronomers must use magnitude numbers larger than 6 to describe such faint stars. These numbers are known as the apparent visual magnitudes, and they describe how the stars look to human eyes observed from Earth. So, tip for the test for the exam, a question that I can ask is, what is the apparent visual magnitude? So the apparent visual magnitude describes how stars look to human eyes observed from Earth. Your interpretation of brightness is quite subjective, depending on both the physiology of human eyes and the physiology of perception. To be accurate, you should refer to flux, the amount of light energy that hits 1 square meter in 1 second. This makes a precise definition of brightness. The simple relationship connects apparent visual magnitude and flux brightness. Are you guys familiar, all comfortable with the term flux? Or should I explain it in a bit of a better way? Okay, so let's see. There should be a whiteboard app on here. Let's see, yes, a whiteboard. Can everyone see the whiteboard? Okay, so we define flux as the amount of light that goes through an area that's 1 square meter. So that meaning this distance is 1 meter, and this distance right here is 1 meter. This will give us 1 square meter. So if we have a light source on a one end and we draw invisible light rays, so the more light rays that penetrates the surface of 1 square meter is called flux. So when we say the higher the flux density, the more of these lines or the light, what's the best way to describe it? You can think about it as vectors that's invisible. The more of these penetrate through that plane, the higher the flux density is. And the less that goes through that plane, the less the flux density is. You guys understand this definition of flux? So one thing to keep in mind that was discussed in the videos, let's see if I can clear this. Is, where is that now? Let's draw this the other way around. So here we have 1 square meter, but let's say we increase that. So here we have 1 square meter, that's further away, 1 square meter, another square meter, another square meter. Here we have our light source again. So when you're closer to the object, so we'll do this, 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 we'll do this. So what that means is the closer we are to the object, the higher the flux density will be because more light goes through that plane. But the further we are away, the less light will go through it. So here we have now 1 square meter. Here we have 4 square meters. So that is known as the, let's get another color, 1 over r squared rule. So if we are 1 meter away from an object, that will be 1 over 1, and that equals 1. But let's say we are 2 meters away, then the flux density is 1 over 2, and that equals 1 over 4, sorry. And that is 0.25. So that means that our flux density is now a quarter as it was 1 meter away. So if we go to 3 meters away, that is 1 over 9. If we go to 4 meters away, that's 1 over 16. So that is how further we are away, there's less flux we are receiving from that object. Are you guys happy with this explanation? Awesome. So let's go back to our lecture slides. So that is the short definition of what flux is. So in a way, modern astronomers can measure the brightness of stars to high precision while still making comparisons to observations of apparent visual magnitude that go back to the time of Hipparchus. So this is one of probably 4 formulas you need to know for this module. It's not math intensive, it's 4 or 5 equations that you will use. This is one of them. So astronomers use a simple formula to convert between magnitudes and fluxes. So modern astronomers has defined magnitude scale, so the 2 stars that differ by 5 magnitudes have a flux ratio of exactly 100. So what that means is when you look in the magnitude scale, when one star is magnitude 1 and the other star is magnitude 6, that means it differs by 5 levels of fluxes. That means the flux ratio of that will exactly equal 100. So therefore we can write it as the ratio of 1 divided by the ratio of B equals 100. So therefore the 2 stars that differ by 1 magnitude must have a flux ratio that equals the 5th root of 100. So that is for one of these steps, which is approximately 2.51 if you calculate the 5th root of 100. So now here we have a table corresponding with magnitude difference and flux. So if there's no magnitude difference, the flux ratio is 1. 1 magnitude difference, the flux ratio is 2.51. And so it continues. You guys happy with this explanation? Okay. So let's go through an example. So this is a question I will ask in the semester test and exam. It's going to be straightforward like this example. So if you know how to do the example, you will know how to do it in a test and exam. So suppose a star C is third magnitude and star D is ninth magnitude. What is the brightness ratio? So what we do is with this brightness ratio is the magnitude difference is 6 magnitudes. So one thing we can do is if you have the table, we can look at 6, that is 251 is the flux density. But the other way we can do it is making use of this formula. So we have FA over FB, so we want that ratio, equals 2.51 times the magnitude of B minus the magnitude of A. So then here is D. D is what magnitude? So D is ninth magnitude, C is third magnitude. So in this equation, we literally plug in over here 9 minus 3, and that equals 6. So it's 2.51 to the power 6. And that will give us our answer. And that answer, do you have a calculator quickly with you? What does 2.51 to the power 6 gives us? Yes, 250 point something. So if you round it up, that is 251. And that's the answer we are looking for. So it's straightforward. So now we can do it the other way around. So if the magnitude difference is 6.32 magnitudes, what is the flux ratio? So the flux ratio must be 2.51 to the power 6.32. And the pocket calculator tells you the answer 336. So the flux from star A is 336 times larger than the flux from B. So now that because of the way magnitudes are defined, star A has the larger flux and numerically smaller magnitude. Now, on the other hand, when you know the flux ratio and want to find a magnitude difference, it's convenient to rearrange the previous formula and write it as follows. So now we have the magnitude difference, or we don't have the magnitude difference. We want to calculate what is the magnitude of each of these stars, but we know what the flux ratio is. So now we just rewrite this formula in this notation to solve for the magnitudes, and we can calculate it. You guys happy with this? So I have some connection problems. The flux is the same as, no, the flux is not the same as the magnitude. So the magnitude is how you perceive it on the logarithmic scale with your own eyes. And flux is how much of those light penetrate or falls onto 1 square meter. So if we go back, so the 2.5 is just part of a formula, yes. So we go back a couple of slides. We define when something is, they differ in 5 magnitudes. So let's say one star's a magnitude 1, the other star's a magnitude 6. That means they differ in 5 magnitudes. And that 5 magnitude has a flux ratio of exactly 100. So if you want to have it for 1 flux ratio, that is the 5th root of 100, and that gives us 2.51. So for this formula, we literally have this formula over here. So that's 2.51 for 1 flux ratio, and then you just plug in everything else. It's a pleasure. So let's go through another example. The light from Sirius has 2.4 times as much flux, so that means 24.2 times brighter than the sun, and brighter than the light from Polaris. What is the magnitude difference? So the magnitude difference is 2.5 times the logarithm of 24.2, which written as 2.5 log 24.2. The calculator tells you that the logarithm of 24.2 is 1.384, so the magnitude difference is 2.5 times that, which is 3.46 magnitudes. So can you quickly show the flux formula again? So when we go to that formula, This is the formula that we need to know. So FA over FB equals 2.51 to the power MB minus MA. What does FA and FB mean? So FA is the flux from star A, FB is the flux from star B. MB is the magnitude brightness of star B, MA is the magnitude brightness of star A. Does that make sense? Awesome. So when we do this equation right here, we're going to use this formula right here. So here the flux ratio is given to us and we want to calculate our magnitude. So that's a straightforward example. So then go to the second example for a second. Yes. Okay, second example, what do I need to explain or how can I help? No, just summarizing. Okay, cool. So what's happening here is for the third example, we use this formula right here. So for the third example, the ratio is given to us, but we want the magnitude difference. So here we solve the magnitude difference. So it's straightforward plug and play equations. So the next thing we need to talk about is the sky and its motions. So when you think about the sky and its motions, which patterns do you guys think about? Or what have you observed about the night sky? What patterns and motions does it make? Any ideas? Things uncertain, they are elliptic. Yes, so what is one of the easiest things we can observe? Think about your assignment. What does the moon do? It has phases, but besides having phases, it orbits Earth. Yes. And what else can we observe that has motions? The Earth orbits the sun. The other planets orbits the sun. The sun orbits the center of our Milky Way galaxy. So everything fits together. So ancient astronomers believed that the sky was a great sphere surrounding Earth with stars stuck on the inside like thumbtacks in a ceiling. Modern astronomers know that the stars are scattered through space at different distances, but it's still convenient to think of the sky as a great starry sphere enclosing Earth. The sky appears to rotate westward around Earth each day, but that is a consequence of the eastward rotation of Earth. Note the rotation produces day and night. Notice how reference points on a celestial sphere, such as the zenith, nadir, horizon, celestial equator, and north celestial pole and south celestial pole, define the four directions: north point, south point, east point, and west point. So for a test in exam, I will ask you, what are these points? So the most important points to remember is zenith. So the zenith point is directly straight upwards. So if you go outside right now and you look directly upwards to a 12 o'clock position, that is zenith. Then the opposite of that, down the earth into 6 o'clock position as nadir. And then we have east and we have west, we have north, we have south, and we have the north celestial pole and the south celestial pole. So astronomers measure angular distance across the sky as angles and express them as degrees as arc minutes and arc seconds. The same units are used to measure the angular diameter of an object. So is zenith above your position all the times? Yes, zenith is above your position at all the times. So it depends basically on your reference frame, but yes, zenith is above you all the time. So for example, in astronomy, when you move or operate a telescope, and you say you're pointing your telescope towards zenith, that is the point directly above the telescope. So are we supposed to know the diagram? No, you're not supposed to know the diagram. Only I will ask you perhaps in a test, what is zenith? Then you have to explain what zenith is. So astronomers might say the stars was 2 degrees from the moon. Of course, the stars are much further away than the moon. But when you think of the celestial sphere and pretend that all celestial objects are attached to it, you can measure the distance on the sky as an angle. The angular distance between two objects is the angle between the two lines extending from your eye to the two objects. Astronomers measure angles in degrees, arc minutes that are 1/60th a degree, and arc seconds that is 1/60th of an arc minute. Using the term arc avoids confusing with minutes and seconds of time. The angular diameter of an object is the angular distance from one edge to the other. The sun and moon are each about half a degree diameter, and the bow of the Big Dipper is about 20 degrees wide. So what you can see in the sky depends on your latitude. For example, if you live in Australia, you could see many star asterisms and constellations invisible from North America, but you would never see the Big Dipper. But you never see the Big Dipper. How many circumpolar constellations you see depends on where you are. Remember star Alpha Centauri? It is in southern sky and isn't visible from most of the United States. You can just glimpse it above the southern horizon if you are in Miami, Florida, but you can see it easily from Australia. So where we are on Earth, depending on our latitude, so that means how far north you are up and how far south you are down. Depends on what you can see in the night sky. For example, let's say we are standing directly here on the North Pole. Then where we can see on the horizon this side, over here, and in any way in these directions. Meaning we cannot see below the latitude line 67.5 degrees. So that's why in Africa we can't see the northern lights over us. That's one of the reasons. But the only reason why you can only see the auroras, you can only see from latitudes that are very north and very south. So when you are at very north, so when you are around about this position, and I would say 45 degrees here, and 45 degrees there, then you can see the auroras. Because what happens is, remember, Earth has a magnetic field that goes like this, from north to south. You're all familiar with this magnetic field? And what happens is the magnetic field is its weakest where it emanates from the north and goes back in itself. So that means this area right here and this area right there has the weakest magnetic field. So that means high charged particles from the sun can enter the magnetic field at those points and interact with molecules in the upper atmosphere. And that interaction of the high charged particles with the atmosphere causes the aurora lights. And that's why you're only able to see them at very northern latitudes and very southern latitudes. Does that answer your question? Awesome. So depending on where we are, will depend on which stars we can see. So say, for example, we are on the equator, then we can only see stars in this direction, and anywhere here. So if we are, say this is where Africa is, that means we can only see stars in this field right there. So depending where we are on Earth depends on what we will be able to see. So this is where I differ from a bit of your other lecturers. The goal of science is to understand nature, not memorize definitions. So I've assumed in your math modules, have you guys done proofs or started with proofs of different formulas? Do you enjoy doing the proofs or not really? Now, I also don't enjoy the proofs. It is important to do the proofs because then you understand where the maths comes from by making use of those principles. But that is where I differ from your other lecturers, especially from the math and applied maths departments. If you've seen a proof, you've seen a proof. So unfortunately, with maths, the majority of your question papers will be to do proofs and show where proofs comes from. I don't believe in that because my argument is if you've seen a proof, you've seen a proof. You're not going to sit in practice one day doing a calculation by starting out with the proof. You're going to use the result of the proof. So yes, it's good to know where the proof comes from, but it's stupid to test someone's knowledge on the proof. You just in any case going to use the result. So what makes a good scientist, engineer, programmer is not your ability to memorize formulas, but rather know where to go look for that formula and how to use it. But I know people from the maths department is going to hate me for saying that. So many people, without thinking about it much, assume that stars are not in the sky during daytime. The stars are actually there day and night. They are just invisible during the day because the sky is lit up by the sun. Also, many people insist that famous star Polaris is the brightest star in the sky. It is actually the 50th visually brightest star. You now know that Polaris is important because of its position, not because of its brightness. In addition to causing the obvious daily motion of the sky, Earth's rotation conceals a very slow celestial motion that can be detected only over centuries. So one thing is, so when you ask people in the northern hemisphere, what is the brightest star? They would say it's Polaris because that's the brightest star in the northern hemisphere and it's the northern star, but it's not the brightest. So the brightest star we can see is Sirius. And that's just something on a side note. And just also on a side note, why is the sky blue during daytime? You guys have any ideas? Reflection of the ocean? Unfortunately not. And that is a misconception that people have. And that is that I say it's the reflection of the ocean. That's not a reflection of the ocean. So atmosphere absorbs the other colors. Yes, that is correct. Unfortunately, not the reaction to ozone layers. So if you are physics majors, somewhere you will learn about the Rayleigh scattering principle. So basically what happens is the Earth's atmosphere acts like a prism. So you all know when you shine the white light through a prism, it is broken up into the colors of the rainbow. The Earth's atmosphere does more or less the same thing. It, when light from the sun enters Earth's atmosphere, the molecules and particles in the atmosphere scatters the light. So it scatters the blue and the purple part of the light spectrum, and the rest of the light comes through. So while it's scattering, that's why the atmosphere in the daytime looks blue, because the blue light is scattered all around and the rest is let through. that's just something interesting as a side note. So addition of causing the obvious daily motion in the sky, Earth's rotation is connected with a very slow celestial motion that can be detected only over centuries. More than 2,000 years ago, Hipparchus compared positions of some stars with their positions recorded nearly 2 centuries previously and realized that the celestial poles and equator were slowly moving across the sky. Later, astronomers understood that this motion is caused by top-like motion of Earth known as precession. If you have ever played with a gyroscope or top, you have seen how the spinning mass resists any sudden change in the direction of its axis of rotation. The more massive the top and the more rapidly it spins, the more it resists your efforts to twist it out of position. You may recall that even the most rapidly spinning top slowly swings its axis around in a circle. The weight of the top tends to make it tip over, and this combines with rapid rotation to make its axis sweep out of shape in a cone. This motion is precession. So to summarize this, if you play around with a top, you'll have your rotation of axis, but you'll see the top point of the top won't rotate directly upwards, or it will always be at an angle, and that angle will spin around in a circle. And Earth's axis does exactly the same thing. So over centuries, Earth is canted at 23.4 degrees, but this cant is also actually over centuries moving in a direction around in a circle. Does everyone understand this, or should I try to explain it a little bit better? Okay, so let me see if I can explain this a little bit better. So let me quickly see if I can find a video that can explain this a little bit better. Because this is quite important to understand. Let me see if I can quickly find something that will help. Okay, I find a video that will try to explain this better. So I'm quickly gonna, is that the reason behind the seasons? Yes, and we will come to that as well. So I'm gonna show you this video.
Under a dark sky, you can see thousands of stars. If you watch for a few hours, you can see them rise as the Earth rotates once a day. And if you go outside the next night at the same time, you'll see that things look pretty much the same as they did the night before. The stars rise and set thanks to the north, and so one day hardly makes any difference to the sky's appearance. But what if you wait for another night or a week? If you're that patient and observant, you can spot subtle changes in the sky. Let's say weeks have passed. Remember that star that was just over a tree in the east when the sun set? The one that made you first notice the stars are rising and setting? Go look at it again. If you happen to be out at the same time, you'd expect that star to be in the same place. But it's not. It's actually a bit higher above the tree. And if you look west, stars that were well off the horizon just after sunset last week are now lower. If you wait a month, this effect is even more pronounced. All new constellations will the sun, literally changing our viewpoint on the sky. The Earth takes a year to orbit the sun once. Every day, it moves a little bit along its orbit. And as it does, from Earth's perspective, distant stars appear to move their positions relative to the sun. So one day we might see a star very near the sun, but the next day the angle is a bit bigger. At some point, about 6 months after we first saw it, the star is directly opposite the sky. Until after a full year, the cycle repeats. What this means to you, the naked eye observer, is that the stars appear to rise and set at different times over the course of the year. Stars in the east rise about 4 minutes earlier every night, and stars in the west set 4 minutes earlier. A constellation that was entirely below the eastern horizon at sunset one month might be completely visible after sunset the next month. Another way to think about it is that the stars appear to be fixed, and as the Earth circles the sun moves through the stars over the course of the year, making a complete circle around the sky once per year. The path it takes is a reflection of the Earth's path around the sun, a line in the sky. We call that line the ecliptic. That means the sun passes through the same constellations in the sky every year. We give those constellations a special name, the zodiac. Every year during a given month, the sun will appear to be in a certain zodiacal constellation, from Sagittarius through Scorpius, Libra, Virgo, Leo, Cancer, and the rest. Eventually, over a year, the sun returns to Sagittarius and the cycle starts again. But even though we talk about this process in terms of the sun's movement, it's really the path traveled by the Earth that creates this effect, as our perspective moves with it. And of course, the planets move in the sky as well. Mercury, Venus, Mars, they orbit the sun too, and they do so in approximately the same plane the Earth does. If you could see the solar system from the side, it would look flat. So to us on Earth, the planets go around the sky over the course of a year, and they also appear to change their positions relative to the sun and stars. The inner planets, Mercury and Venus, move so rapidly you can see their motion after a single night. The outer planets are more leisurely, but wait long enough and they too will be seen to move, sliding through the constellations. By the way, the word planet is Greek for wanderer. There's another aspect of all this you might notice over time. You've probably seen a globe and noticed that the axis of it is tilted. That is, it's not straight up and down, perpendicular to how it sits. That's because a globe is modeling the Earth, and the Earth is tilted. The Earth spins on its axis once per day and orbits the sun once per year. But the Earth's axis is tilted with respect to its orbital plane by 23.5 degrees. And this has a profound effect on our planet. Imagine for a moment that the Earth's axis were exactly perpendicular to its orbit, straight up and down. If that were the case, every day, the sun would take the same path across the sky. If you were on the equator, the sun would rise, go exactly overhead, and then set. If you're on the pole, the sun would appear to go around the horizon every day, neither rising nor setting. It would always be twilight. But that's not the case. The Earth is tilted. In the months of June and July, the Earth's north pole is tipped toward the sun. 6 months later, it's pointed away. This affects the path the sun takes across the sky. Instead of it taking the same path every day, in the northern summer, when we're tipped toward the sun takes a higher path in the sky. Because that path is longer, the days are longer too. 6 months later, in December and January, the Earth's pole is tipped away. The sun takes a lower path in the sky, and because the path is shorter, days are shorter too. That's why we have seasons. When the sun is up high in the sky, it shines straight down on the ground, heating it better. And days are longer, so it has more time to heat us up. It gets hot. In the winter, it's the reverse. The sun is lower, so it can't warm us up as efficiently, and it has less time to do so. It gets cold. There you go. Seasons. The Earth's axis is tipped. If it weren't, the seasons wouldn't occur, and the temperature of the Earth wouldn't change month to month. There's a common misconception that the Earth has seasons because it orbits the sun on an ellipse, and so it's closer to the sun in summer and farther in winter. While it's true the orbit is elliptical, Earth is closer to the sun in January, on the order of 5 million kilometers or so, than it is in July. It's the angle of the sun's rays that makes winter cold and summer hot, not our distance from the sun. Also, you may know that when it's summer in the northern hemisphere, it's winter in the southern. When the North Pole is tipped toward the sun, the South Pole is tipped away. So northern and southern hemisphere seasons are opposite each other. But nothing in astronomy is permanent. The North Pole's not always going to point toward the sun in June, and Polaris is not always going to be the North Star. That's because our planet's axis is actually moving. Have you ever seen a spinning top start to wobble, its axis moving in a slow circle even as the top itself spins? This is called precession, and the Earth does it too. Our planet spins on its axis once per day, but the axis wobbles, making a very slow circle that takes 26,000 years to complete. This affects a lot of what we see in the sky. For example, Polaris won't always be the pole star. Every year, the pole points a little farther from that star, making a big circle 47 degrees across. For ancient Egyptians, the star Thuban was the pole star, and in about 11,000 years, that position will be held by the bright star Vega. Also, the date the sun is in a particular zodiac constellation changes slowly due to precession as well. When the ancients first thought up this idea, the sun was in Aries on March 22nd. Vernal equinox, what some people call the first day of spring. But due to precession, it's now in Pisces. That's why your astrological sign doesn't match where the sun actually is in the sky. 2,000 years of precession has changed them. One of the many reasons astrology is silly. It's incredible to think about. The Earth, the sun, the stars. They allow us to tell the time and time of year just by looking up and paying attention. This is why the stars were so important to ancient humans. The stars were like a clock and a calendar in the sky, long before we had invented either. We've actually learned a lot about the sky just by looking at it. Of course, some of the stuff I've explained we've learned through other means. The Earth is spinning, stars have different intrinsic brightnesses, and so on. But all of that, far more, got its start by people who went outside and looked up. Later, as we applied math and physics to what we observed, we learned even more and could then go back and explain what we saw. So don't discount naked eye astronomy. It's all we had for thousands of years. In fact, I think we lost something when we started using clocks and calendars and moving to cities with bright lights that washed away the stars from the sky. Those folks long ago were tied to the sky. They knew it like you know the streets in your neighborhood. They could see the stars rise and set. They knew the glory of the Milky Way sprawled across the heavens, even if they didn't know exactly what it was. We do know now, with our knowledge gained over the centuries. But it comes at the cost of losing touch with the sky, not living under it as much as we once did. I've spent thousands of hours over my life at night just simply looking up, watching the stars, appreciating the universe as I can see it. The things I have witnessed have shaped my life and instilled in me a permanent and endless sense of wonder and joy. The universe belongs to everyone. Go outside, and if you can, soak up your share. Today we talked about
Does that explain the concept of precision better? Awesome. So let me just quickly get the slide where we were on. So as you can see, in the top points of our planet Earth moves in a circle. That's called precision. So for a test and exam, I might ask, what is precision? So Earth spins like a giant top, but it does not spin upright in its orbit. Its axis is tipped at 23.4 degrees from the vertical. Earth's large mass and rapid rotation keeps its axis of rotation pointed towards a spot near the star Polaris. And the axis would remain pointed constantly in that direction except for the effects of precision. So you might ask, what, for an exam, I might ask, what is precision? So what we're talking about right now, what is precision? So over centuries, precision has significant effects. Egyptian record shows that 4,800 years ago, the North Celestial Pole was near the star Turban. The pole is now approaching Polaris and will be closest to it in approximately the year 2100. In about 12,000 years, the pole will have moved within 5 degrees of Vega. So figure 2.7c shows the path followed by the North Celestial Pole. Next time you glance at the famous star Vega, remind yourself that it will be someday be a very impressive North Star. So here we can see where it started out as Turban. Here we are Polaris, then that's the path of the Celestial Pole and how it will move around. So now we're going to start with the next chapter, and that is chapter 3. And that is the cycles of the sun and the moon. So what do you know? What cycles does the sun and the moon make? Yes, so when you go back, that was the star. So that is the northern star directly above the North Pole. So 4,000 years ago, that was Turban. Right now, currently, that is Polaris. And in another couple of thousand years, that will be Vega. So what cycles does the sun and the moon make? Revolution, rotation. So it's zenith. So yes, if you're standing on the North Pole, Polaris is zenith. The moon spools the oceans, yes. But let's go to even easier. So the cycles of the sky are elegant and dramatic. And you can understand them fully only if you know that Earth is a moving planet. Yes, sir, you raised your hand. So zenith is not always above the North Pole, it depends where you are. So if you are outside, zenith is directly above you. Pleasure. Mr. Madia, so isn't the sun white? No, that is a bit of a misconception. The sun doesn't appear white. If we are, that's just due to our atmosphere. So with our atmosphere, like we said, it appears blue and a lot of light gets reflected. But if you observe it, this is what it looks like. Our star is a red giant that we will talk about in later chapters. But here we can see different activity of sun. So here, the images at above, we can look at a sun in the visible part of the spectrum. Here below, in the infrared part of the spectrum. Do you guys know what these little dots are on the sun's surface? That is sunspots that we will cover in a later chapter. But basically what that is, that's an area on the sun or small piece of area that is cooled due to its magnetic field lines that's now extending through that region. But the more sunspots you have, the more active the sun is. So in this top region, you can see a lot of sunspots. If you look at the ultraviolet, you can see the sun is very active. If you look at this image, you can see no sunspots. And if you look in the infrared, you can see the sun is not active. And that is different cycles of the sun that we will learn about. And then as well, you've all probably looked at the phases of the moon. Can one of you explain what is the phases of the moon? Not Earth's shadow, it's the moon's own shadow. So we're seeing the moon at a different angle, and that's the moon's own shadow that we are seeing. And that follows a 28-day cycle. Yes, I've seen you raised your hand. Maria, you can unmute yourself and ask a question, or you can type it. Okay, let's continue. So Earth's rotation on its axis causes the cycle of day and night, but it is its motion around the sun in its orbit that defines the year. Notice an important distinction. Rotation is the turning of a body on its own axis, but revolution means the motion of a body around a point outside of its axis. Earth's orbit is a nearly perfect circle, but it is shown in an inclined view in this diagram, and consequently looks oval. Earth's motion around the sun makes the sun appear to move against the background of the stars. Earth's orbit is just projected on the sky as a circular path of the sun, the ecliptic. If you could see the stars in daytime, you would notice the sun crossing in front of the distant constellations as Earth moves along its orbit. So the ecliptic that we see is the path the sun makes in the sky. That path will differ depending on are we moving into summer or winter. And that means the more sunlight we receive, the less sunlight we receive. And this is what's meant with the zodiac. So when we are here on Earth, we are January 1, we look at the sun, and it looks like we're looking towards the sun, that the sun is in Sagittarius. Or if we are the 1st of March and we look towards the sun, it will seem like the sun is in Aquarius. And that continues on. So if we are here and pointed this way, the sun will be in Gemini. If Earth is here and we look towards the sun will be Leo. Do you guys understand where this comes from? And something interesting, due to precision, the zodiac keeps changing. So currently, that's people, astrologists talk about it, is astrology is rubbish. This notions of the moon and the sky and where the sun is and what constellation does not do a thing. And currently, due to precision, the zodiac signs are incorrect and should be adjusted for. But that's just something on a different side note, and something that irritates me that people have a superstition such as astrology. So please make the difference between astrology and astronomy. So astronomy is the science, astrology is rubbish, gibberish. So the apparent path of the sun against the backdrop of stars is called the ecliptic. If the sky were a great screen, the ecliptic would be a shadow cast by Earth's orbit. That is why the ecliptic can be described as the projection of Earth's orbit on the sky. Earth circles the sun in 365.26 days, and consequently the sun appears to circle the sky in the same period. That means the sun traveling 360 degrees around the ecliptic in 365.26 days travel about 1 degree eastwards in 24 hours, about twice its angular diameter. And you don't notice this apparent motion of the sun because you can't see the stars in daytime. But it does have an important consequence that you do notice the seasons. Earth will not experience seasons if it rotated upright in its orbit, but it does have seasons because its axis of rotation is tipped 23.4 degrees from its perpendicular to its orbit. Another way to say is that Earth's equator is inclined 23.4 degrees to its orbit. Because Earth's axis of rotation is inclined at 23.4 degrees, the sun moves into the northern sky and spring into the southern sky in the fall. That causes the cycle of the seasons. Notice how the vernal equinox, the summer solstice, the autumn equinox, and the winter solstice mark the beginning of the seasons. Earth's elliptical orbit is very nearly circular, and as it travels from perihelion to aphelion, the distance from the sun varies only slightly and is not the cause of seasons. Earth goes through a cycle of seasons because of changes in the amount of solar energy that Earth's northern and summer hemispheres receive at different times of the year. Because of circulation patterns in Earth's atmosphere, the northern and southern hemispheres are mostly isolated from each other and exchange little heat. But one hemisphere receives more solar energy than the other, and it grows simply warmer. So what's meant with these equinoxes as when we are moving around the sun, the way it is tipped, the vernal equinox is March 20, and that is when the sun will be directly above that point. So the vernal equinox, so we'll read about in South Africa, that is the Tropic of Capricorn, then the sun will be directly above it. Summer solstice is June 20 in the northern hemisphere. And then the autumn equinox is on 22 September. Winter is on 21st December. So on 21st December, that will be summer in South Africa. So what is meant by this tipping? So how are we allowed to call it spring equinox? So in the southern hemisphere, we will call it the opposite. So not spring, we will call it autumn equinox. So when northern hemisphere have winter, the winter solstice, we have the summer solstice. So just the opposite around. So here we can see the Earth is tilted. So here is the northern hemisphere, here is the southern hemisphere. So here we can see more light is reaching the northern hemisphere during certain types during these 6 months, and that is why they are summer in the northern hemisphere and winter in the southern hemisphere. But going 6 months later, we can see that the southern hemisphere receives more sunlight than the northern hemisphere, and is what causes summer, winter, autumn, and spring. Are you guys happy with this explanation? Do you guys have any questions so far? How do flux play into this? That is a very good question. So, if let's get our whiteboard out again. I'm going to clear this. So let's draw. Let's see. This is Earth. Here is the. Let's draw this bigger. Here is Earth. Here is our angle, 23-degree angle that's tipped. So let's say roughly 23 degrees. And on this side, we have the sun. So in the southern hemisphere, we have more light hitting Earth's surface per square meter than in the northern hemisphere. So that means the flux density in the southern hemisphere is higher than the flux density in the northern hemisphere. And 6 months later, the northern hemisphere will have a greater flux density from the sun, and the southern hemisphere will have a less flux density, and that is what causes the different seasons. Does that answer your question? It is a pleasure. So let me get back to the slide. Do you guys have any other questions? So if you don't have any further questions, then I think we will call it a day because the seat period is ending in 2 minutes. If I will remain active for another minute or two, if you guys have questions, thank you very much for attending this lecture. I really appreciate the interaction in the class. I really appreciate it. If you have no questions, then I will see you all in tomorrow's class. I will upload this lecture and provide links to the videos I've shown. Have a wonderful day, guys, and I'll see you all tomorrow. Yes, we had 2 formulas, and there's about 4 formulas you will know for this lecture. Sir, are there any past papers available for this module? Unfortunately not, but I will give you a mock semester test and a mock exam for practice. It is a pleasure. Yes, I've seen you raised your hand, Wiley.
So I was wondering whether when we're being tested for this, will it be more theoretical or practical?
Theoretical. So I would ask you what is a few definitions, explain certain concepts, list what are some of Galileo's most important discoveries, for example. And then one or two calculations from the formulas and the examples we did from the textbook.
Thank you.
It's a pleasure. Am I pronouncing your name correctly, Mr. Jarrett? Yes, you can unmute yourself and ask a question. No, no worries. Sambulo, you ask a question, you have your hand raised. The slide depends, it all depends on your lecturing style. If my slides are quite thorough, if you think that will be enough for you, then you're more welcome to just use the slides. If you want to go deeper into everything I'm teaching you, then you can get a textbook. So we can practice on your own. Yes, you can. I will upload the mock tests and mock exam closer to the test and exam dates. Please give us practice activities every now and then. Yes, I will. So I will give you quizzes that you do online every now and then. It's a pleasure. So it seems like there's no further questions. So have a wonderful day, everyone, and I will see you all in tomorrow's class. Yes, I will provide you with a formula sheet. It's a pleasure. I'm also going to log off now. Have a wonderful day, and I'll see you all tomorrow.